Hi everyone, welcome to another Leetcode problem discussion. Today you are going to talk about problem 994, rotting oranges. Well, this is not among the blind 75 list, but I like this problem because it explores different concepts from graph, and also it explores a very common technique about solving problems, like looking at all different scenarios along with the common scenario. So let's go to the problem discussion. We are given a m into n grid where each cell can have one of these three values. So we have a grid or a matrix. So it has three values each cell. Each cell can have three values. It can have 0. 0 represents an empty cell. 1 represents a fresh orange, and 2 represents a rotten orange. Okay, so every minute a fresh orange that is 4 directionally adjacent to the rotten orange becomes rotten. So that means if there is a rotten orange and it can actually rot the other neighboring oranges, that means in 4 directions. So left, right, up and down. Okay, so but it cannot rot an orange diagonally. That's the important thing. So we have to return the minimum number of minutes that must elapse use until no cell has a fresh orange. If this is impossible, we have to return -1. Okay, so we are given a matrix. Each cell has each cell can have three kind of values. 0 means that cell doesn't have any orange. 1 means it has a fresh orange. 2 means it has a rotten orange, and a rotten orange can uh, infect its neighboring oranges in 4 directions. Okay, so we have to find, and this rotting happens in 1 minute. So the neighboring fresh orange becomes rotten in 1 minute. So we have to find the minimum number of minutes. So here is one example. You see the given values here are like 211. So you see this is 211 and 110 and 011. Okay, so you can see according to the picture, if I had put the values, it would have looked like this. So I have to find out like how much time it will take to get all the oranges rotten. Okay, and if that is impossible, if there is a fresh orange left, in that case I have to return -1. Okay, so looks like it's a graph problem, right? So in a graph, what happens is if you consider each of these are nodes, right? This node has like four neighbors, right? So these has edges to the neighboring nodes, right? So it can actually, this is actually a graph looking like this, right? Okay. Okay, so let's convert this problem, make it a little bit like rotate it 45 degrees, the same thing, like the same thing here. I'm just rotating it 45 degrees to make it more visible. So one important thing to notice here is each of these cells are nodes, right? Nodes of a graph. And you see, we know that each cell is connected to, or it can infect only the neighboring cells in 4 directions. So if there is a diagonal thing, so this is not an edge, this is not a valid edge, or this is not a valid edge, okay? Or this is not a valid edge. So these are not valid edges. For the valid edges, let's put them in green color. So this is a valid edge. This is another valid edge, right? So this one has edge to the top, to the left, to the right, and down, similar to the right. So these are the edges of the graph, right? Yep. Okay, so we have drawn all the edges, and think each orange being a node. Okay, so we have to, solving graph problems, we have to find out, starting from a rotten orange, how can we get to the other fresh oranges? So since this is a graph problem, we know that the graph problems actually can be solved using DFS or BFS. Now, the thing is, DFS actually goes uh, depth-wise, right? So it goes to the depth. So for example, here you see for this picture, the first two oranges that are going to be rotten are this and this, right? Okay, so we want to explore the neighbors first. If we want and if we want DFS, you know that DFS actually instead goes, say, in the, like, it explores the depth, right? Okay, or maybe it can go like this way and then come here and then come here. Instead, if we use BFS, then we make sure that this one is like visited first. These two are visited first, right? So that means BFS actually visits the neighbors first and then goes to the next step. That means for this problem, actually, we can also solve this by modifying DFS a bit, but the natural selection for this problem is BFS. Using BFS, we can actually go to our neighbors uh, earlier than the further nodes, right? Okay, so BFS is a good, I think, the good algorithm to solve this problem. So as you see that from time 0, this is time 0, right? And then at time 1, this node and this node is going to be explored. So that means these two, from fresh oranges, this one becomes rotten, right? Okay, in time 2, what happens is this is explored, right? This is explored and this is explored. So through these edges, you see this one gets infected or it becomes rotten. So this one becomes rotten in time, in second. Uh, Also, this one becomes rotten, right? So this is from time 2. There was a chance to rot an orange here, but there is nothing here. So nothing happens here. Okay, so this is in time 2. And then you see this orange is going to rot this in the next step, right? So this, and also this, both this one and this one, they could have rot this orange, but there is nothing here. So this one becomes rotten in second 3. And finally, this one becomes rotten in time 4.
Let's start looking from BFS perspective. So in BFS, we will have a queue, right? And initially at time 0, this orange is going to be in the queue, right? This orange is going to be in the queue, okay? And then we have to take this out and put its neighbors. So you can see by the blue edges, we can see the neighbors, the two of the neighbors, they're fresh. So you'll put them in the queue. So that means they are gone like rotten. And then at time 1, these two will be in the queue, right? So this one and this one is going to be in the queue, right? Okay. And then at time 2, we will take these two out and put its neighbors. So what are the neighbors of these two which got rotten at time 1? This one and this one, right? Okay, so these two are going to be put in the queue. Okay, at time 3, we just take all of these out and then put the neighbors of these two oranges. So what are the neighbors of these two oranges? You see that this neighbor is not existent, but this one is. So this is 3, so this is going to be put into the queue, right? Okay, and then this is, we take this out, and then at time 4, we take the neighbor of these orange, which is this one, right? So this is 4. Okay, so in total, we need 4 minutes to make all the oranges rotten. Have you thought about a scenario when you cannot rot an orange because it cannot come into contact with another rotten orange? So here is one such example. In the interviews, you have to find these things yourself because the examples are not given. So the first row in this example is 211.
So 2 means it's a rotten orange. I'm just drawing the oranges. 1, and 1, and then 0, 1, 1. So this is empty. This is an orange. This is an orange. And finally 1, 0, 1. That means this is an orange. This is empty. And this is another orange. Okay. Okay, and as you see the first one, this one is empty, right? And this is rotten, sorry. So at time 0, this is empty. At time 1, you can see this one becomes rotten. This one tries to be rotten, but there is nothing here. So okay, so there is nothing to be nothing to rot here. Then this one at time 2 makes this one rotten. At time 2 makes this one rotten, right? Okay, next you see this one and also this one, both of them can rot this orange at time 3, right? And then this one actually tries this way, there is nothing here. It tries this way, there is nothing here. Okay, next, as you see, this one rots this at time 4. Okay, and okay, so that's the only way. As you can see, this is not reachable. So that means this is not reachable at all. That means after we run our BFS, we have to make sure that to scan the whole grid to see if still there are fresh oranges. If there are fresh oranges, then we have to return -1. Then another scenario is what if uh, none of the oranges are like say, or say all of the oranges are already rotten, right? So what if all the oranges are already rotten? So here you can see one example here. So there are like two given are like two values. So empty and then there is one. And this one is also rotten orange. So as you can see that there are only two places and this there is no other orange to get infect, right? So there is no other orange to infect. That means already all the oranges, whatever oranges here are rotten. So at time 0, all the oranges are rotten and then that's the answer, right? Now let's think about another one. Uh, let's say if multiple oranges are rotten at the beginning, say at time 0, two of the oranges are rotten. And in the previous example, we had seen that this two became rotten in time in minute 1. This one became rotten in minute 2. This one became rotten in minute 2, right? Okay, and this one became rotten in minute 3. And finally, this one became rotten in minute 4. Okay, but this time you see that actually all the rotting is not obviously going to happen from the top, right? So this one is also a rotten orange. So if this is at time 0, actually this will rot at time 1, right? Okay, and then this one from both sides, even this one may infect this, or this one may infect this, or this one. In all three sites, this one will rot at time 2. That means instead of 4, this time uh, all the oranges will get rotten in time 2. That's another thing to notice here. That means we have to scan the whole graph, and at the beginning, every rotten orange, so this one has to be put into the queue, and this one also has to be put into the queue. So we have to initialize the queue with all rotten oranges so that we make sure that both of them keep on rotting oranges and at the same pace to its neighbors. Okay, so you see like multiple scenarios, and this is a learning for any kind of algorithm. You should consider all kind of scenarios and ask the interviewer and then incorporate them into your solution. Okay, so let's code this. So let's we'll for BFS we need a priority queue. Sorry, we need a queue actually, and inside the queue we have to put the uh, grid cells, and the grid cells is a combination of row and column, right? So we put an integer array, and then we'll have a time int time equals to, we'll put it as -1. I will tell you why. And initially what we are going to do is we have to scan all the rows and columns, right? Because we have to check if any cell value is already 2, that means it's in rotten orange, then we put it into the queue. Okay, so we put the index of the row and the column into the queue. Okay, next, so we have initialized the queue with all the rotten oranges. Then we have to start our BFS. So while this queue is not empty, then what we have to do is we have to increase the time. That means, yeah, so that is the minute, right? And what we have to do is we have to, uh, like, for a particular minute, like we have to take out all the oranges in the queue and put their neighbors for the next minute, right? So let's take in size of the queue, and then we'll take out all the oranges for that minute that are rotten at that minute, right? The position of the rotten orange in the queue. This is in particular the row, and this is the column of the rotten orange, current rotten orange. And then I have to check if this orange is able to infect its neighbors. So if row less than, okay, not only that, I also have to check and if the neighbor, so I'm checking it so that I'm not going out of bound, right? Out of bound of the row. If my right neighbor is already fresh, then what I have to do is I have to uh, make it rotten, put into the queue. Okay. Okay, so I will keep on doing this in different formats. Let's copy paste this a few times. So I will go in 4 directions. So I'll go in 4 directions. Okay, so then I will check if my row is greater than 0. And can I go left? And my left neighbor is still fresh. In that case, I will infect my left neighbor and put it into the queue, the rotten orange. Then I'll check the column. The column length is not still out of bound. Then I will go down. And finally, if the column value is still greater than 0, then I will go up. So finally, what I have to do is I have to return the time. But before that, I have to do another scan, right? I have to scan if I see still there are oranges that are fresh, that means they're unreachable. So one means fresh orange. In that case, I will return -1. That means I couldn't rot all the oranges. Finally, we return the time, but before that, I have to tell you something. You see, initially you had put the time as -1, and if, say, there were like no rotten oranges, in that case, this while loop will never, we'll never enter this while loop. And even if we like escape this, that means there were no fresh oranges. So that means there are no fresh oranges, there are no rotten oranges, so time still remains -1 here. In that case, it means that the grid or cell was like empty, right? Totally empty. In that case, we have to check if it still remains -1. That means the cell or the grid was totally empty, so we have to return 0. Otherwise, we return the time, right? Okay, let's run this. This accepted. And submit it, and you see this was very fast. So what is the time complexity of this algorithm? So this time complexity of this algorithm is the order of the BFS. So it's order of, because every cell is visited, say once, right? Put into the queue once, and in the worst case, it is put into the queue once and taken out of the queue once. So they're like order of m into n cells. So they're like m into n cells, so the time complexity is going to be order of mn.
Is a space complexity. In the worst case, all the oranges are rotten, and initially we put everything in the queue, and the size of the queue becomes mn. So space complexity is also order of mn.
Okay, so that's it. Thanks for watching, and we'll come back with another problem.